Okay, so this is going to be a lecture on light, and we're going to talk about the refractive index, lenses, and mirrors. So, basically, when light travels through a medium, its velocity is lower than it is in a vacuum. So what do we mean by that? When light goes into glass, it actually travels slower than it does through a vacuum. And we have an equation that gives us the ratio of that relationship. So C is the speed of light in a vacuum. V is the speed of light in the medium. So this could be glass, it could be hydrogen peroxide, it could be whatever. The bottom line is that when you take this ratio of the speed of light in a vacuum to the speed of light in the medium, you get this value n. This is known as the refractive index. We'll get into a minute what refraction actually is. But this is a very important thing to know, that the refractive index is the ratio of the speed of light in the medium. The ratio of the speed of light in a vacuum relative to the speed of light in the medium. So we say glass has a refractive index of 1.5. That does not mean light travels 1.5 times faster in glass. It means it actually travels 2/3 of the speed that it does in a vacuum. So if glass has a refractive index of 1.5, if you divide the speed of light in air or in a vacuum, we usually approximate the speed of light in air as the same as the speed of light in a vacuum. So if we divide those two, we'll get this value 1.5. So C over V is 1.5. Therefore, C over V is 3 over 2. So if we take the reciprocal of that, we can get the ratio of the speed of light in the medium over the speed of light in a vacuum. So in glass, light travels 2/3 of the speed that it does in air or in a vacuum. And so what is refraction? So I'm going to show you this quick diagram. So what we have here is a light ray. What's happening to that light ray? So remembering just going back to high school or middle school physics, usually what we think when we think that when light reflects, it bounces. Just like that, bounces off the surface at an angle where θ1 equals θ2. But when light transmits, and it's able to transmit through a medium, something special happens. The light slows down. And when light slows down, what happens is that the light bends towards this dotted line. So this dotted line is known as the normal. And so what is the normal? So the normal is 90 degrees to the surface. As you can see, 90 degrees there and 90 degrees on the other side. So this light comes in at an incident angle of θ1. Then it bends towards the normal, so the light ray gets closer to that dotted line. I've drawn it as a solid line just for convenience, but I'll make it dotted again. So that's what's happening. The light is bending towards that normal line, where θ1 is greater than θ2. So if you have an interface between air and a more optically dense medium, when we say optically dense, it means it has a higher refractive index. The light slows down and bends towards the normal. Now, in the opposite case, where light slows down in the glass, let's just say this is glass, and goes back to air, as you can see, it's going to now bend away from that normal line. So this is what you can see clearly here, that once it leaves the glass, it speeds back up, so it bends away from the normal. So this angle gets bigger. So let's do an example question, and where we can learn a new equation. So a beam of light strikes the surface of hydrogen peroxide, H2O2, which has a refractive index of N equals 1.414. And it makes an angle of 30 degrees to the surface. What angle does the refracted beam make with the normal? So we're going to learn a new equation here. So Snell's law is going to form a relationship between the incident angle, which is the angle it strikes the surface with, and the refractive angle, which is what it makes with the normal once it slows down. So N1 sine theta 1 equals N2 sine theta 2. So where does that equation come from? How do we get that equation? So this is known as Snell's law, which is what I mentioned before. And one thing that you can do now is pause the video and see if you can actually derive this equation, understand why it works the way it is. But here's how we can think about it. Snell's law is simply saying that if you multiply the refractive index of air or a vacuum, which is typically the case you see it in, but it could be any other case. The cases where Snell's law is applicable, by the way, are quite diverse, because you can also use Snell's law when light goes from a slower medium to a faster medium. But bottom line is that this value here, N1, right, that's just the speed of light in a vacuum relative to the speed of light in air. So we approximate that as C over C, which is just 1. So the refractive index of air we approximate as 1 is equal to N2 sine theta 2. And so that is hydrogen peroxide. So what that means is this is the speed of light in a vacuum relative to the speed of light in hydrogen peroxide. And so this relationship here, if you just multiply it, that keeps things constant. And typically that's how you see equations in physics. You know, constant equals constant. So yeah, that is Snell's law. Now another thing that I would like to mention is the following. And that is this. The wavelength of light, lambda 1, over the wavelength in the medium is equal to so what that means is that if you have medium 1 and it goes into medium 2, then you can use this relationship, right, to see how things change. The bottom line is that if we remember this equation, V equals F lambda, the wavelength must change in order for the velocity to decrease. So in the medium, if the velocity has decreased, then another parameter, and in this case it's the wavelength, must also decrease. The frequency of the light does not change in the medium. So make that clear. Yeah, just wanted to check the microphone's on. Okay, so back to the question. Enough rambling. So let's go ahead and compute this. So we had the air hydrogen peroxide interface. So hydrogen peroxide had a refractive index of 1.41 sine theta r, which is the refracted angle, equals 1 sine 30, because 30 degrees was the angle it made with the boundary. So the sine of the refractive angle, sine theta r, is equal to sine 30 all over 1.41. And so arc sine 30 all over 1.41, that is our refractive angle, which is 20.7 degrees roughly. So that is a pretty simple example. Now you understand where the refractive index comes from, what it actually means, and you've learned about Snell's law. You've also learned about the fact that what parameters change when light slows down in the medium. So that is the wavelength. I cannot stress enough that on the MCAT there could potentially be a question where they say which parameter changes when light enters the new medium, and you would be wrong to say it's the frequency. So that's the main thing. So let's move on to the next section, which is where we are going to discuss more about this refracted phenomena. So here we go. Now, we've talked about refraction, but surely light doesn't just refract, light also reflects. So let's have a look. If you're under the ocean, and this is you, and this is a ship, and you're looking to that ship, there might be a case where you can't actually see that ship. Now, why is that? That's because instead of light reflecting off the ship, what's happening is because of your angle, it refracts off the water. Because if you think about it, the reason we see things is because light reflects off things. So if the light is refracting, then you're not going to be able to see the light. So here we have the water. And then we have air. So when light leaves that medium, it's going to refract. And notice the direction of these arrows. This angle here, theta 2, is bigger than theta 1. That is because it's speeding up as it exits. But surely that wouldn't make sense, because you can be at the bottom of the ocean and you can see something at the top. You should be able to see a ship. So light isn't just going to refract. There is actually going to come a point where the light begins to reflect off the ship. And this is known as the critical angle, which is when you are at a boundary. There is an angle between when you're going from a index of refraction of higher to lower. So essentially, when you're going from the scenario where light is going from a slower medium, talking about the velocity of light, to a faster medium, so it's going from glass to air, not air to glass, there comes a critical angle in which instead of refracting, the light will reflect. Now, what is that angle? That angle is known as the critical angle. And so when you are at the critical angle, exactly on the critical angle, this is what happens. So there's your boundary. The light goes 90 degrees, just like that. That's what's happening to the light. And it's at the critical angle. Once you exceed that critical angle, it reflects. So that's how, if someone is underwater, they're able to see the ship on the surface. Now, how do we calculate the critical angle? So the critical angle is actually done in the form where you can get it from the refractive indexes. So what that means is the following. If you take the ratio of the refractive indexes when light is going from the slower medium to the faster medium, and you take that ratio, then you get the critical angle. So in this case, n1 is greater than n2. So if we want to find the critical angle for light going from, for example, glass to, water to air, right? So what we would do is we would take n1 and n2, so sine theta critical, is equal to the refractive index of air, which is 1, over the refractive index of water. And so the arc sine of that that's equal to the critical angle. And that is the angle in which light is going to reflect rather than refract at the boundary between water and air. Hopefully that makes sense. So next we're going to talk about lenses. And lenses are a big topic on the MCAT.